Okay, so our next speaker is Cécile Gachet from University of Bochum, and she'll tell us about motivating the effective cone conjecture.
Thank you for the introduction. It's a great pleasure to be here in Taipei for the second time. I'm very thankful for the invitation and for everybody who spoke before. I had a great time listening to all the talks. Today I will talk about some joint work with Shui-Yung Lin, our host here, Isabel Stenger in Hanover, and Long Wang, who I think is in Fudan right now, about the effective cone conjecture. So let me maybe just, as you figure, it's about cones, right? So for any x, so we're working over C, mildly singular. Okay, so normal projective variety. Some point q factorial will be nice. For now, we don't need it maybe too much. You can associate some cones. Cones that are, so you can associate some even, so convex, non-degenerate cones in finite dimensional vector spaces by just looking at various notions of positive divisor or positive one cycle modulo numerical equivalence. So typically, probably the most famous one is going to be the Mori cone of curves. I'm going to keep everything closed for now. The Mori cone of curves in the space of one cycles, which is a finite dimensional real vector space. You also have its dual, that's very popular. That's the Neff cone that sits in the Néron-Severi space of divisors, and these are pretty famous because of this very successful story with the cone theorem, developed by Mori and then by some other people, like Sharpen, to have more and more application, I think late 70s and throughout the 80s. But there are actually more cones. So popular one for birational geometries is a movable cone. So you have move x. I'll always put a bar. I'm always going to take it closed by cone. So closure of the cone spanned by movable Cartier divisors. And of course, since you're taking a closure, what happens on the boundary is very much not movable Cartier divisors in general, so you're still in N1 XR. And another famous one is, well, you have an effective cone that's sitting in there as well. So this one, I'll keep this notation for the genuine effective cone, and then you can also take its closure. So this one, the spanned by effective let's say codimension, okay, let's say effective Cartier divisors again. And its closure F bar X, the pseudo-effective cone, right? Great, so we have a lot of cones. This has been studied, for instance, and possibly introduced by Kawamata in the 90s. Something really interesting about this one is that it packs information about X as well as other minimal models of it. And I'll talk about this a lot. This is part of the topic of the talk. And for curves, by the way, you also have other cones that you can study, strongly movable one cycles and so on, but this is not the topic today. And you can also have, these cones come with natural group actions. So groups acting on X and induce actions on N1, preserving those cones. So the typical ones are, well, you have the automorphism group that's going to preserve pretty much everything we defined. So you have the group of birational transformations, but that's not going to preserve most of that in general. So let's forget about it. And then one of the groups that we'll care about today is this group of pseudo-automorphisms. So they're birational self-maps from X to itself. So birational that are isomorphisms in codimension 1. So you can toss out something of codimension 2 on both sides, and you get an isomorphism. Great. And so the topic of today is the or a cone conjecture, which is a statement about the interplay between those cones and those groups. Not in the Fano case, that's already very much covered by this cone theorem, but in the boundary Calabi-Yau case, as well as in the pair setting. So if you don't know pairs, just think of regular Calabi-Yaus. So let me state cone conjecture. So usually attributed to Kawamata and Morrison. And I'd say around 94 or so would be. So let X delta be a KLT Calabi-Yau pair. So in KLT I include that X should be Q factorial. Then the first point should be that the group of automorphism of X that preserves the support of the divisor while it's acting on the Neff cone of X, which is a closed cone. Okay. But of which we remove a little bit, and I'll talk about this in a second. Or we could also view it as Neff modified by removing a little bit in another way, and I'll come about it in a second. So this action on this cone has a rational polyhedral cone, so a rational polyhedral fundamental domain. And so here I can add maybe to my list of cones for any cone in N1 on XR, that's a convex non-degenerate. Non-degenerates, I define CE to just be, well, you keep your cone C and you just keep the effective things within it. So C intersects F X, and as this effective cone is not necessarily closed, this is not necessarily a closed cone. And I'll define C plus to be, well, okay, let me maybe ask for the cone to be closed. If I didn't put closed, just take the closure before you do the operation. And so here you only keep the genuine effective things on the boundary, and here you're gonna only keep the genuinely rational things in their convex hull on the boundary. So you take the convex hull of C intersect with your lattice, with your Q structure coming from Katia or Val divisor, whichever, right? So, okay, so first statement is that this should have a rational polyhedral fundamental domain. And here you see why I need to modify the Neff cone, as if we don't modify the Neff cone, there's kind of no chance to get larger than this. And then there's so that was the first statement, I guess 93, and then there's a second improved statement made by Morrison following work of Kawamata here. That's a similar thing for the movable cone and the pseudo-automorphism group acting. So that's it. So this is a conjecture. To be precise, the Kawamata version is with the effective part, the Morrison version is with the plus part, but if you believe both are true, then actually the cone should be the same. And if you believe non-vanishing, the cone should be the same anyways. So let me just pack it in the conjecture just to have a neat formulation, because I'm going to explain the equivalence of this conjecture with other ones, so I'd rather have everything kind of neatly stated. And so maybe a remark. That's a bit of a motivation Plus, okay, let's say criticism is the motivation of this is very strong from the point of view of birational geometry. And so something very interesting, for instance, is if one holds, then it means your variety X will have finitely many fibrations up to the action of the automorphism group. X has finitely many fibrations modulo precomposing by some automorphism. And so in particular, also finitely many birational, like elementary birational contractions, so finitely many extremal birational contractions, birational, so extremal birational contractions, say. Which of course is much weaker than this, because not everything that you see in the cone fabricates a contraction, but this is still very interesting if it were to be true.
In the statement, it should be auto, not auto x delta, auto x.
Depends who. Totaro put x delta. I agree that we should put auto x, but
your statement starts with x has a finitely many fibration. So it should be x.
then it would be modulo auto x delta. I mean, if there's x delta here, then there's x delta here, right? Sorry. I put it part of the conjecture. It's not known sadly. It's well in dimension 3 maybe, but you know, in dimension 2 definitely. It's some like non-vanishing thing. It would be, so I'll speak about it. One inclusion is known here, and then if you assume MMP and good minimal models, then it's fine. I put it in, so this is my second remark actually, thanks. So my second remark is that, so as we said, 2 is kind of a bit nicer because it's not just information about X and morphisms starting from X, but also birational morphisms starting from X. So 2, and so that's the thing, is something that would be nice is if 2, since the movable cone contains all the nav cones of the models, 2 should imply some finiteness on minimal models in the same spirit as 1. That's not exactly true. I'm going to need to add some assumption here. But the point is, so here it's some result by, I think I read it in Cascini and Lazach first, 2010 also, is that if you put 2, so this movable cone conjecture, plus, okay, here you need assume existence of good minimal models in dimension X, in dimension D, so in dimension equal to the dimension of X, then the movable cone conjecture would imply that X has finitely many, okay, so if delta equals 0, it would be X has finitely many minimal models. So there's finitely many ways you can turn this, did I? Yeah. This scalar B, the Turner scalar B are manifold into something else. And if in general it would be some statement, in general there are finitely many well, okay, there are finitely many minimal models for the pair X delta, but this is the same as saying there's finitely many ways to turn X into something else by an isomorphism in codimension 1. So there are finitely many target varieties x1 until xn for small, okay, so for birational morphisms x dot 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 xi onto something q factorial that are isomorphisms in codimension 1. So there's finitely many things you can get from X. So let me maybe, okay, I'll come to an example in a minute. The typical example was something like this, a street if you start with something Fano. As you take something Fano, it happens to be a Mori dream space, and I'll speak about this back, then there's finitely many targets you can get from it. If you're Fano, it's great because there's not just finitely many targets, there's also finitely many ways you can move away from X. In this case, maybe not, but there's finitely many things you can arrive to. But the sadly, okay, so that's the very good part, is if you like, stick to that if you like minimal models. But then in general, the sad part is this conjecture would have interesting birational implications provided, with a little bit of extra assumption from MMP. And so today's talk, yes? Yes, because I'm closing it. So I forgot to put the bar here, but I'm closing every cone. So the closed version is contained the closed version. Yeah, I think I wrote it for move, closure of the cone spanned by. Yes. So sorry, so here I closed, because all the construction I closed before doing E and plus. Well, these aren't closed then, of course, but for instance, Neffy is in movie, because the close and then you intersect and so on. Great. So today is about comparing these conjectures plus, introducing a similar state. So it's very easy to write similar conjectures. You just put any cone, put a reasonable group, and make the conjecture, right? So you could do it for the effective cone, but maybe it's a stupid conjecture that's trivially false. So similar conjecture for effective cone. The effective cone of devices, right? And relating that to the previous ones. So maybe we'll need to assume some MMP type statement to do this. Maybe under assumptions on MMP, existence of good minimal models. Okay, on MMP working. So that would mean technically at least having something in small dimension. And also ideally, I think some good motivation for me to do this comparison and see when or what do you need MMP is that you have an F-cone conjecture and a movable cone conjecture, and they don't seem so good in the sense that maybe you should add some abundance to have something like this. Maybe you should add some extra MMP to be able to say something from this conjecture. So maybe there's one, it could be that there are some better conjectures that implies the others, just unconditionally, so it would be stronger, but that's assuming MMP is equivalent. Then it would mean you have a conjecture that somehow maybe doesn't entail MMP, but that's stronger than all these two conjectures, and that, anyways, we all believe MMP is true, and you would be equivalent. So then maybe it's a better thing to work with, because if you work with something stronger like this, you don't need to assume MMP all the time. You can try to prove it or not, right? So this, and also the goal is there a strongest form of cone conjecture? So I don't know if, first you would have to see which cone, which group, etc., which modification, implying all other forms, all other statements, and implying back under if MMP, if assuming MMP. I think everybody knows here, but I know there are some younger people, so if you've never heard about MMP, just think of it as you start with your variety X, and you take any effective divisor, and so effective, of course, you might have negative intersection with some curves, and you don't really know what's going on. And so MMP is just, people hope there should be an algorithm that starts with your divisor and then performs some flops and some contractions until anything that was negative in intersection with your divisor is just contracted, and now everything's positive and great. Or maybe you did a fibration and put this in the fiber. So that's MMP, and then assuming existence of minimal models is just assuming you can run and terminate the algorithm. Good minimal models is you run the algorithm, you terminate it, and then the thing that's positive, that's not, you know, this divisor you get at the end that's not negative, it's a pullback from a non-isomorphism. So it's just, that's what it's, yeah, that's MMP in one sentence, I guess. So that would be really nice. And maybe a motivation for this is not just this abstract knowledge, but an additional motivation is to not compare this conjecture as conjectures for all x, but compare them for any given particular x. So that say, oh, I have a particular Calabi-Yau variety, I want to prove the effective cone conjecture or the movable cone conjecture. Can I just prove some Neff cone conjecture and then I'm done or not? So additional motivation would be okay, I guess otherboard would have been a better. Let's put it here. Additional motivation. On a fixed variety, on a fixed pair, so KLT Calabi-Yau pair, X delta, can we relate cone conjectures and prove one form of it? So, for instance, the Neff cone conjecture from proving it, you know, from explicit study of another better behaved another cone, so typically move, say, that we can compute from geometry. Can compute. So very explicitly geometrically by just characterizing everything and finding rational curves and flopping them. And so, oh, this is stuck, okay. And so for us, I think starting working with Shui Young, I mean, you can ask him, maybe he disagrees, but that was very strong motivation because, okay, maybe this is not a good idea, but movable cones are quite hard to compute in general. Effective cones tend to be easier because to find some boundaries in the movable cone, well, you have to find some movable divisors, and that's not always easy, unless they're Neff and you're lucky. But to find some effective cone that are extreme, and in the effective cone, it's very easy. You just have some exceptional divisors or something. And so you already have some candidates for your cone, and then computing it is generally easier. So here maybe I can write something that's probably quite reasonable. Is F is usually easiest. Neff is not so hard if you do it for X itself, but if you do it for another model, well, you have to understand your flops, so it's quite hard. And move, and yeah, so here, that could be interesting, but here if you try to understand move from F, that would be quite nice already. But of course, if you do put move and move here, it's not interesting. So, I think I don't want to, I see lots of people frowning, so I don't want to keep the suspense too long, so I'll just state the main theorem, and then I'll spend a lot of time, yeah, especially in the second row. I'll just state the main theorem so you know what it is, and then I can explain an application and also explain why you should expect this. And the reason you should expect it is if you know what a Mori dream space is, just listen to the main theorem and think about X being a Mori dream space. And, and it should be quite evident what's going on. So there's a little bit of numbering, so let me just get my notes. So I'm going to start by writing up 5 statements, and then I'm going to explain what are the implications between them. Right, so X delta is a KLT Calabi-Yau pair. Consider the following statements. So we'll stick to the usual one. So one is going to be the same as we had in the cone conjecture. So this Neff conversion. So OT, but a little bit more than that. So OT is going to be OT X prime delta prime acting on Neff E of X prime, which we hope should be Neff plus X prime, has a rational polyhedral fundamental domain. So this is our PFD. For all X prime delta prime obtained from X delta by an SQM, so by a birational isomorphism in codimension 1. So this for short will write SQM. So with X prime, the Q is for Q factorial. All right. So we're assuming the Neff-Kohn conjecture not just for X, but for all of its other minimal models. And also the set, so one would be A, and B the set of all such X prime delta prime. So all such X prime delta prime modulo the, okay, actually just like that, is finite. So here we're assuming Neff-Kohn conjecture for all the models and finiteness. If you think about the Fano variety, well, this is true for the Fano, if you put the Fano. For the other models, it's not so obvious, but it's also true because it's a Mori dream space, and I'll come to that in a second. So that's 1. 2 is, okay, this was the worst. Now 2 is going to be much easier. 2 is just a movable cone conjecture. So psot X delta, and just for X itself, acting on move E equal move plus, has a rational polyhedral fundamental domain. Then, okay, let me skip 3 for a minute. Three is going to be an auxiliary one just, to make your implications loop. So let's just not worry about it for a second. 4 is going to be the effective cone conjecture. So psot X delta acting on Fx equal F plus X has a rational polyhedral fundamental domain, right? Now maybe I can put 3, but it's an auxiliary one, so let me maybe just put it in a lighter color. So 3 is just going to be some intermediate between 2 and 4. So here we're asking to have a fundamental domain in this movable cone that, using the group, allows to cover the whole movable cone. Here we're assuming that we have a fundamental domain in the effective cone that allows to cover the whole effective cone. So an intermediate statement would be to have something in the bigger cone that allows to at least cover the smaller one. So that's just 3. So 3 is just auxiliary. So it's just going to be, there exists pi, a rational polyhedral cone inside the larger one, such that when you use a pseudo-automorphism group to try and cover something with your pi, well, at least you cover the smaller thing. So you're in between here and there, right? So it contains the interior of move. So you can think of your pi as, for instance, okay, I'll write in a sec, but for instance, it should be obvious that 4 implies 3. Because in 4, you have something in here that covers the whole effective cone, so it's already going to cover the interior of the movable. So here I can already write 4 implies 3, right? And also, here you can see also that 2 implies 3, right? 3 is just a bit weaker, because 2, you have your pi, that's in your movable cone. I thought it's in the effective cone, and it covers the whole movable cone. So it's okay. So 3 is really just auxiliary. 3, I mean, you can probably guess from the statement, is that 2 and 4 are going to be a bit hard to compare, but 3 is just right below the 2 of them. And so 5, maybe now it's the one where really you have to think really hard about Mori dream spaces, is that for the movable cone, somehow 1 and 2 are related because the movable cone encapsulates all this information. And so now the question is, what does the effective cone encapsulate? And the answer is, it encapsulates all the information about X, its minimal models, and also birational contractions, where you really contract divisors and decrease Picard number. So 5, so we'll, let me maybe define. For a birational contraction from a variety X, we don't need the divisor here really, from a variety X with maybe some flops to a variety Y. So you might think of you just running a whole MMP if you want. We introduce some component that sits in the effective cone and that encapsulates a bunch of divisors from here. So we're going to keep the pullback of the nef cone. I'll keep E on here to stay effective, plus the sum of just some positive rays, so we toss in some positive rays for each exceptional divisor. So where the set of the EI are the exceptional, so the prime exceptional divisors. All right? And so let me just give this a name. We're going to call this F, because it sits in the effective cone. It sits in the effective cone of X, so we'll keep that in mind. And then we're going to put the contraction here, just to keep in mind it's whatever in the effective cone of X comes from this divisorial contraction. And so what I want to put as number 5 is in the same way. So in the same way that you think of the movable cone as containing all this information about the nef cones, you can think of your effective cone as containing all this information about the birational contractions. So here I want y to be q factorial as well, just so I can pull back, okay. And so 5 is going to be the same as 1. Yes? Yes, thank you so much. Yes, yes, yes. Thank you, because you pull back from downstairs. And so 5, so I mean, the second statement, you can guess what it is. It's going to be something like all search pairs y delta y. The set of all of them is finite. And the A is going to be if you look at the automorphism group of X delta, because you're upstairs, that leave your F equivariant acting on this particular piece. So sorry, I should put it, yeah. So has a rational polyhedral equal F plus. So again, we pack in the abundance. Has a rational polyhedral fundamental domain. I'll give an example of all these codes in a minute. Let me just finish the main theorem. So far we just have a bunch of different statements with already some implications. So let me just write the conclusion. So what are the implications between these? Our statement is, first of all, that looking at the pieces of the Neff cones, or the pieces by this, so this we'll call Maury chambers. So our first part is that looking at each of the Neff cones separately, because, I mean, this contracts divisors. I guess here I'm contracting things in codimension, I'm flopping only, and here you'll have flops and divisorial stuff. So you can think of a map, you know, this is a blow-up of Pn, and this is Pn, right? Yes, absolutely. And birationally, it's an isomorphism, but okay, I understand what you mean. No, the point of a contraction is that the inverse of F does not contract divisors. So this means F inverse has no exceptional divisors. So for instance, if you think it's a standard Cremona involution, that's not okay because it contracts stuff. Has no exceptional divisor. So the map from Pn to its blow-up is not okay. Thanks for the question. So then, the point is whether you have the Neff pieces or these funnier pieces that we just introduced, doesn't matter, these are equivalent. So whichever pieces you look at, these are the same. Now the other good point is whenever you have these pieces, you can always glue these and 5 together to get your effective cone back, without assumption. So if you have the Neff cone for the pieces and 5, you get it back for the effective guys. So okay, I have an equivalent, so I can put this one here, but it's a consequence of the others, right? So now, I'm just going to put back the other two that we have. So we had that 3 was just some auxiliary thing that we have at the bottom of the diagram. So far we really have a pretty clear, two clear winners is that 1 and 5 are much stronger than the other two, without assumption. And now the point is maybe we weakened a bunch of stuff. So what I just want to explain is now if you assume a little bit more of MMP type things, you're going to get an equivalence. And so the point is here to connect here to have 1 implies 2, we only need to assume something very mild. So 1 implies to us to glue the Neffs into the moves. So to glue the Maury chambers into effective, we can do without assumption. To glue the Neff things into movable things, we only have to assume. So here is assuming that move E is in move plus. And if you prefer, you can assume MMP. MMP for X, so I mean for any pair put on X. Okay? So here 1 implies 2, you have it, but you need a small extra condition. And so now we still have 1 and 5 above, so we need something from downstairs, ideally 3 back up, and we have it here. But here we're going to need the big condition, because sadly we need 1. And so star is going to be assuming existence of good minimal models in the whole, not just for X, but for everything of dimensions in as dimension X, assuming existence of good minimal models in dim and equal to dmax. So, you know, we had to make a sacrifice. So now the great news is if you just put this assumption, all of these are equivalent. So maybe in dimension 3, yes? MMP implies this. Yes, exactly. Yeah. It's just that I promised, usually I would just write this, but I promise it's related to MMP, so I have to write it. But yes, precisely. So it means you start with any KLC pair, you can run an MMP, it terminates, and after it terminates, whatever this nef thing you're left with is semi-ample, and you can get your Mori fiber space. So it's pretty strong. So we can weaken this. So maybe here a remark, but this is not going to be very helpful for most people. I mean, I don't think. So if you know what you know, then good for you, but nota bene is in lieu of star, it suffices to, I guess because you're asking, so you know what it means, that's already good. To assume geography of ample model works for X itself. Works on X, and I'll say a word about this later, and you can also translate it into some finite generation, but this is all very MMP intensive, so I don't want to get into it too much. But so at least if you want to put an assumption that's just on X, you can do it. But maybe let me add one more remark here, is that something really nice, you might want to do this. So basically so corollary is assuming, so in dimension up to 3, all 5 statements are equivalent. So if you like threefolds, and for threefolds there's a lot of work to do because this is all completely open, then you can view it whichever way you like, they're all the same. So you prove one, you prove all of them, right? And so maybe a remark that's kind of motivated by a question that Sasha asked in Paris, because I gave a similar talk, is a remark is something I don't know how to do is if X is smooth hyperkähler, it's not clear that we have the all equivalents. Do we have all 5 equivalents? And so here there's kind of 2 catches. Well, the good news is for hyperkähler we have MMP. We can run them from a hyperkähler and they terminate. So that's great. But we don't have this good part in the MMP. So that's bad news. So we can't, so for hyperkähler we have the yellow thing, but we don't have necessarily the red thing. And the other problem is if we start with a guy that's smooth hyperkähler, then it's great to run MMPs from it. And maybe if you suppose it's K3 and type, you can even have good minimal models. But the thing is we don't just want, red is not just good minimal models for X, that's your hyperkähler thing. It's good minimal models for X and everything of the same dimension. So even for hyperkähler of dimension 4, I'm not sure. And I don't know. And maybe part of the remark is somehow the question should be like, how strong is it to ask for the smaller assumption on geography? And as far as I know, you have to really check in BCHM, like how you can generalize the argument in particular places. And so that's, everybody in this line of work are saying, oh, this is just BCHM and general, a bit more general or something. So I tried, I'm not sure. And I'm not sure if it's, yeah, so I'm not sure if you can apply it to hyperkähler and if you can weaken star or make it somehow a little bit nicer than this and less like MMP intensive. But at least, so somehow in dimension 3 we can really work with this. Because everything's equivalent, so put everything under the rug and you're okay. And in dimension higher, then if you work with a particular X, at least you have everything except the red one, usually. If you have some extra stuff. Great. So I think now is maybe a good time to make just a drawing to illustrate all these cones I introduced, right? So What time did I start? Ooh, so it's already 45 minutes. Right, great. So an example for all these cones. Yes, of course.
At the beginning you introduce the closure of the F cone, and then it's
Uh-huh.
never used. So is this in your theorem? Is it a closed effective cone?
No. So, okay, so it's the open, and I guess I should put a bar. The only place I kind of use it is here, right? Because I define plus only for closed cones. But no, because if it's closed cone, it's never going to work. I mean, unless you have some stupid automorphism, you know, for an abelian variety, think abelian variety. Like, if you close it, then you have all this irrational stuff on the round boundary, and you're never going to get it from anything. For all the notations. And so maybe this is a good time to credit that a lot of this in the name Mori chamber is inspired by this paper by Hu and Kiel about Mori dream spaces. So you take, and so the example is from notes by Cinzia Casagrande, who taught some summer school about Mori dream spaces. On Mori dream spaces, and they're quite well explained, so I think I really like the example, and I think it's quite minimal, so I can just draw it on the board and you can see what it is. So start with X. Fano is going to be the blow-up of P3 at 2 points P and Q, so 2 distinct points. All right. So the Picard rank is 3, so I can just draw some triangle into plane. So here's a picture. That's going to be the effective cone of X, which is going to be equal to the closed one, and equal to the one with the plus as well. So they're all the same, it's great. So what do you put in the effective cone? Well, you're going to have the exceptional divisor above the point P, the one above the point Q, and the proper transform of a hyperplane passing through P and Q. Right? And turns out that's all, so that's the effective cone. Now if you care about the Neff cone, well, that should be okay. So you're gonna have, so you're gonna have pullbacks from the base, so from the P3, sorry. So you're gonna have H. So H is going to be a pullback of OP3 of 1, right? HPQ was the strict transform of a hyperplane through P and Q. So this guy is Neff because it's a pullback of Neff. And another thing you can do is pull back some hyperplane, but that just goes through one of the 2 points, right? So here you have HP, that's the strict transform through one of the 2 points, and here you have HQ. That's the strict transform through the other of the 2 points. So now I can draw the Neff cone inside here. So you have your whole effective cone, that's the whole thing. The Neff cone is just going to be this. So this is Neff, 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 and the sums are Neff as well. And so now the movable cone, well, it turns out you actually have this also in it. So this is going to be actually Neff cone of another model of a model of X. And how do you get this model? So say X prime, you just flop the lines through P and Q. So flop LPQ. So LPQ is just the strict transform of the lines through P and Q. Right. So now that's the Neff cone of X, that's the Neff cone of a model. So these two, they're going to be inside your movable cone. And now, do you have more? Well, this one is an exceptional divisor, so there's no way it's movable, right? You can't move an exceptional divisor. This one's same. And actually, whatever is on this side, you can't move it either. So this is going to be your movable cone, the sum of these two. So, sorry, the union. So this is movable cone of X. And so now you see to cover your effective cone, you need a little bit more. And so that's why you're going to have these Fx, birational contraction ones. So X, you see it has a lot of birational contractions because you can contract it. So that's Fp, say you can contract it to just a blow up at one point. You can contract it to just a blow up at the other point. And then, of course, you can also contract all the way back to P3, right? So that's going to be, I don't know, phi. And so these should appear in the drawing, right? Because we defined those chambers, so they're going to show up here. And hopefully they account for everything we couldn't cover before. And, well, the great news is they do. So, well, when you pull back from pi 3, so look at phi. What's the chamber for it? Well, you pull back the nef guys here, so you get your H. And then you add the exceptional divisors, which are here and there. So you get this chamber, right? So this is going to be the chamber back up on X for this contraction all the way to P3. And now the other two, so the little triangles here, this is going to be the chamber. It has the exceptional degree divisor for P, so it's going to be the chamber for FQ. And then this is going to be the chamber, the last one. The effective chamber for Fp. Okay, so somehow here you see that your effective cone encapsulates all this information about the nef cones and the Mori chambers. And it's all kind of packed tightly together, and here you see it's very nice. It's just some triangulation, right? With faces and very familiar picture. So somehow this should reassure you that all these chambers aren't so crazy, that all these different cones aren't so bad. And also it illustrates in one example a very general thing, that if you take all those Mori chambers and you take their union, they should cover your effective cone, or at the, they should cover your effective cone. And if you take all your nef chambers, they should cover your movable cone. And that's not exactly what we proved, to prove that you need MMP, but at least what I can tell you is they cover the interior, because the interior are big divisors, at least, and for those you can run MMP, so they cover the interior at least. So in general, so maybe proposition, in general, the picture is the same, right? We also pave, maybe tile, sorry. We also tile Fx with the, so Fx, maybe let's put interior with the Fxf, with those Mori chambers for all the birational contraction, and move, at least its interior, with all of the nefs, with all nef x primes. And the second part is, at least in dimension 3, it's just a result by Namikawa from 97. And in higher dimension, well, you can also prove it. It's okay. So this if dem equals 3, it's, sorry, Kawamata, my bad. Kawamata 97. Right, so I think I have, if you have any questions, maybe now is a good time. And if you don't, what I will do is I'll just explain how to apply this main theorem to a very concrete example, where we can prove some movable cone conjecture. So. Okay, I'm going to erase the board. Maybe if some questions show up, that's good. It would be a good time too. Yes?
In the example,
Uh-huh.
how to define delta?
Well, that's a good question. X is Fano, so minus kx is ample. So you just take a multiple of it so that you have some sections. But here you can be lazy and not even do that. And then you just take a general section so that you have a smooth divisor and do 1 over m of that. So you can do it, but...
In the case, I think automorphism of X data becomes smaller, but
So that's a good point. It goes smaller, but I think just by a finite index. And so it doesn't change anything for the cone conjecture. So a posteriori, it's kind of an interesting point is that somehow it should be at x delta. I agree, it should be at x, because the delta doesn't appear in the cone, so why should it appear in the automorphism group? But I believe somehow if you have the conjecture for odd x delta, if you can prove it, then a posteriori it would imply that odd x delta is finite index in odd x. If cone conjecture is true for the smaller one, which is very surprising, but at least for surfaces it's true. Because Totaro proves cone conjecture, and you can also prove it by hand, but that's the finite index part. But yeah, okay, so maybe now it's time for application. So here's an example that I think I read for the first time in Schoen 85 and was studied also by Professor Namikawa in 91 and was also studied by Grassi and Morrison in 93. I'll say more of about those in a second. We define X to be so it's going to be a smooth Calabi-Yau threefold. So we don't need to put any delta for this one. And so the way we define it is as a fiber product of two general rational elliptic surfaces. So they all have some maps, some anti-canonical map to P1. And you can also view them at blow up of P2 at 9 points, general, so on a general pencil of cubics. And maybe for, yes. General rational, for me it's in the definition of rational elliptic, but I'll add it, yeah, rational, relatively. Okay, so here maybe we have a relatively minimal, maybe let me put it here. So de facto, you're going to have some singular fibers, but there's just 12 of them and they're just nodal curves, the usual nodal rational curves, so it's not so bad. So that's the thing, and we also want the image, have all 12 plus 12 singular fibers, they should sit above different points in P1. Sit above 24 distinct points in P1. So you shouldn't have rational fibers sitting over the same thing, because then if you take your fiber product, it's not good. But this is just some very mad generality assumption. So you look at this guy, and what is known as the dimension, so the pKa rank is 19. So if you try to draw an F-cone, it's a bit complicated, right? But Grassi-Morrison show that the F-cone conjecture is true. But sadly only for X, not for the other models. And now if you care about the other models, well, Namikawa tells you what they are. Well, he tells you what they are, so exactly what to flop to get them. But then it's not completely obvious what you get after you flop and what's an F-cone there. So the Namikawa paper proved that there's finitely many minimal models, which is great news, because then you could think, well, now I'm going to prove Neff conjecture for them, right? And glue, because it's the strongest one anyways. But the bad news is there's about, so Professor Namikawa provides an exact count, but there's about very many, right? 5 times 10 to the 19. So, so that's not our approach. We don't count that. And maybe also some interesting insight is those models, they all have finite automorphism group. And it's Z to Z twice or once or just trivial. And all of them have finite automorphism group of cardinal at most 4, say. Well, except for X itself. And now X, maybe I could put it near the pKa number. The automorphism group of X up to finite index is just some very large, virtually abelian group, because it comes from model Veil stuff. So Z to the 16, I believe. right? So, and it's, and also, so that's Namikawa as well, proves that OT X, however, is a whole birational group of birational automorphisms of X. So it's kind of interesting because X has a special role, and as far as we know, that's where it stopped, right? So it wasn't clear that movable or effective cone conjecture was known. We've seen it claimed in a few papers, but never with proof. So, I don't know. Anyways, so corollary of our main theorem is, so the corollary is the effective cone conjecture and so that's the first one, but then we actually get all of them, right? Because we're in dimension 3. The movable cone conjecture hold for X, so and both of them. Also, the Neff cone conjecture holds for each of many minimal models. Of X introduced by Namikawa. And maybe a corollary of the corollary is, besides X, all these minimal, so everybody gets the cone conjecture for their Neff cone, but besides X, they all have finite automorphism group. So when you move your rational polyhedral cone by your automorphism group, well, you can only cover, something rational polyhedral. But the cone conjecture is true, so you cover everything. So the corollary is each minimal model of X, except X itself, has a rational polyhedral Neff cone. And even better, it's spanned by semi-ample classes. So it's just exactly what you'd have for the Fano. And I think I should stop here.
Questions, comments?
Yes? Thank you so much. So you allow me to add something, which is great, is that there's some results. So some of the implications had been known very recently. So there's a paper by Li Zhao on the archive, I think 23, that proves some things in the relative case. Then there's a paper by Li himself, right? I think by Li himself, also in 23, that proves a little bit more, like get rid of some assumptions but also in the relative setting. Then there's a paper by a student, I believe, of Birka named Fulin Shu, that actually proves one of our implications, so one of the same implications, and it was on the archive a few weeks before our preprint. So I think it proves moves implies Neff, and some of it is in a relative setting. And then recently there's a preprint by Andreas Höring, Jishin Xie, and Gianluca Pacienza, which generalizes also our results to the relative setting, but with the same methods. But so you have to, and also Höring, this should be read like backwards, Höring, Pacienza, Xie. So there's a lot of, so there's, as you see, it's kind of recent and active. Actually, the only key thing is that we use a lot of convex geometry, not a lot, but some convex geometry to prove our result. And it's stuff that only works if your cone are non-degenerate, so don't contain lines. And in the relative case, if you look at effective cones, they might contain some lines, sadly. And so, but the thing is, if you look at if you forget about this effective cone conjecture, I think these are all okay because the cones are non-degenerate. If you try to add this one in the relative case, maybe it's true, but it's just you have to see how the convex geometry works if you have lines in your cones. So that's a bit problematic. But yeah, so there's stuff.
Why do you need it for all x in given dimension? If you start with a fixed x, how do you use it for other arrangements? Why did you?
So, okay, so what we truly use is, okay, so I explained in the drawing, right, that the effective cone, you can cover it with all these chambers, and also the movable cone with all these chambers. But the only thing we really need is that these decompositions have some local finiteness property. Of the type, if you cut with something compact, actually if you cut with something rational polyhedral, you cut finitely many things, and your intersections are rational polyhedral. And actually this chamber thing is just a geography of ample models. And so, you know, what we want is just that this works for the geography of ample models. And there's some reference, so the reference we use is this paper by Koronia, Kalogiros, Lazic, I think in 2014. And so for them, it's just actually some finite generation of rings of sections on X. And now the thing is, if you want to make it an MMP assumption, then your question is, you know, how much where do you assume good minimal models to have this finite generation of rings of sections, but just on X for any devices? And I'm not sure, because the thing is, the proof that we know for that, the proof we know for that is a paper where they just say, use do the same proof as BCHM, but replace big by effective, and it works the same, kind of, which is not true for all the BCHM paper, obviously. No, but you know, that's kind of a problematic kind of. Maybe there's a good reference that does it. I don't know. If anybody has the answer, I'm very happy to hear it.
More questions, comments?
So, for Morrison space, the equivalence of this detectors are equivalent or not?
For, sorry?
For Morrison spaces?
Yes, so I didn't state it. For Maury dream space, so the definition of a Maury dream space is a Maury dream space is something that satisfies this and also has no erase. So all the Neff cones are rational, oh no, sorry. Okay, yes, I mean de facto yes, but Maury dream space is all your Neff cones of all the models are rational polyhedral and you have finitely many of them.
So this should be not, I mean, the equivalence of the
Yes. So this is, yeah. So I mean, then you don't have to put even the groups. You just put, oh, this is rational polyhedral. But I mean, I guess my point is this is the definition of Maury dream space. Then this comes for free, and then this is a corollary. But you know, you don't even need. So you have finitely many chambers also everywhere from Maury dream spaces. See here, you even had like finitely many chambers, right? Yes, precisely. So all Fanos are Maury dream spaces. Yeah.
That's a weak Fano, right? There's a flopping curve.
I think it's a flip. I think not a flop. Maybe it's. I think it's an honest Fano. You blew up 2 points in P3.
This red line is the node you can contract to non-factorial.
It is K trivial, this line.
I think it's. I'm sorry. I'm tired. Maybe you're right. Okay. Sorry.